Hello students, today we will continue our lecture on chemical kinetics. This lecture is presented by me, Pranit Ghatak, your chemistry teacher. So, let's begin. In this class, we are gonna deal with two things, that is activation energy that is being called as EA, and the second thing is Arrhenius equation. So, we're gonna deal with two things, that is activation energy, which is being represented by the symbol EA, and Arrhenius equation. Okay, this will be the last topic of this chemical kinetics part. Okay, in the next day as well we will do some numericals of this chapter so that we get a clear picture of this chapter as well. Okay, so let's begin. Here the first topic of the day is activation energy. So activation energy is defined as the minimum amount of extra energy that is being required by the reacting molecule to get converted into product. It can also be described as the minimum amount of energy needed to activate or energize molecules or atoms so that they can undergo a chemical reaction or transformation. Okay, so what is being activation energy? So activation energy is basically extra amount of energy that is being required by the reacting molecule to react, to get excited to do the reaction properly. Okay, so as we know, any reaction can be happening between the reactants and the products. Okay, reaction occur from reactants to products. Okay, so reactants they react and products they formed. Okay, so to do a reaction, suppose there is a reaction is occurring between A and B. So A and B they react and they will produce C and D itself. Okay, so C and D are the products and A and B are the reactants. Okay, so the minimum amount of energy they required, the reagents required, the reactants required, that is the A and B required to excite themselves, and by getting excited they will do the reaction. Okay, so it can also be described the minimum amount of energy needed to activate or energize the molecule or atoms of the reactants that they can undergo chemical reaction or transformation. So after getting that extra amount of energy, that is being called as activation energy, after getting the activation energy, the reactants or the reactants molecule they get excited, and after getting excited these reactants will do the reaction properly and form product. Okay, so this is the concept of activation energy, and this activation energy is being symbolically represented by the EA. Okay, by the term EA. Okay, activation energy. Okay, so let's see the graphical representation of activation energy. Here in this slide, in this picture, we can see two things, that is this is the energy level, this is the energy graph, this is the energy graph, and this is the reaction coordinate. That means how much the reaction have been proceed. Okay, so x-axis coordinates the reaction coordinate part, and this y-axis represents the energy. Okay, so here okay, in this violet line I have been describing the energy of the reactants. The energy of reactants is being this one. Okay, and what is the energy of the product? The energy of the product is here. So we can see that the energy of the product is low, and it is very normal, because if the energy, as we know, the stability is inversely proportional to the energy. So if energy is low, the stability will be higher. So in the case of reactants, the energy is higher, so stability is low. But in the case of products, the energy is lower, so stability will be higher. So reactants will go to the more stable form, that is the product form. Okay, so here the stability is low because energy is higher, and here in the product stability is higher because energy is lower. Okay, so this is the corresponding ratio of stability and energy. Okay, so let's get aside from that as well. Okay, so here in the case of reactants need a special amount of energy. Okay, so before we do that, we may know that this is the reactance energy and this is the production energy. This can go for here as well. Okay, the reaction can undergo in this pathway, not moving in this pathway. Okay, because in this pathway they need some extra energy, but the reaction may go in this way. By going in this way, the reagents or the reactants need less amount of energy, but this couldn't happen. Okay, because to do a reaction, reactants need to get excited, and to get excited they need extra energy. This extra energy is being called as activation energy. Okay, so to do the reaction, the reactants need an extra energy, and this extra energy is being conveyed in this way. Okay, and this extra energy is being called as activation energy, and this activation energy is being represented as EA. So this is the cause by which we can define that certain reaction that in normal temperature cannot do or cannot undergo, but when we heat the system, then the reaction goes on. Because if we heat the system, then the reagents or the reactants, they get external heat, or they get this sufficient amount of activation energy from the heating of the system itself. Okay, and by getting the activation energy, they will get excited, and after that the reagents or the reactants will react together and produce the product. Okay, so this is the way of a reaction. Okay, so to do a reaction, the reagents need activation energy. This activation energy is nothing but a extra energy that excite the reagents to do a reaction to form a product. Okay, so this is the graphical representation of activation energy. Please practice it carefully, and you should do it again and again, so that it is become very clear to you. Okay, so let's move to the next topic of the day, that is the Arrhenius equation. So Arrhenius have given an equation based on the activation energy. Here this equation is formulated in this way, that is K is equal to A into e to the power minus EA by RT. K is chemical reaction rate, that is the reaction rate is K. A is called the P exponential factor. Here e to the power means exponential to the power EA, that is EA is the activation energy as we know. Okay, and R is the gas constant, universal gas constant, and T is the temperature in Kelvin scale. As we know, small t is being degree Celsius and capital T is in the Kelvin. Okay, so here we use the capital T. Okay, so Arrhenius equation is basically K is equal to A into e to the power minus EA by RT, where K is equal to chemical reaction rate, A is the P exponential factor, EA as we know activation energy, R universal gas constant, and T is temperature in Kelvin scale. Okay, so here if we take ln in both the side, then what we will get? We will get this kind of form, that is ln K is equal to, here this e to the power minus EA by RT, when we ln into e to the power minus EA by RT, then this E will get cancel out and we will get minus EA by RT form. Okay, so this will come forward, and this is the minus EA by RT plus ln A. Okay, so this will be the logarithm or ln form. Okay, so here if we take and graph between ln K versus log 1 by T. Okay, so how can we get that graph? Okay, so just as we know, we are getting a equation by taking ln or log in the both the side, then we will get a formula like this one. That's EA by R into 1 by T plus ln A. Okay, this is the logarithm form, but we can use it and we can write it in another way. That is, if we write, okay, we can write it in this way as well. A by R into 1 by T plus ln A. Okay, so here we can compare it with another equation, that is the equation of a straight line, that is y equal to mx plus c, where this m corresponds to minus ea by r, this m corresponds to ea by r, this x is 1 by t, here this x is 1 by t, and c is ln A, and here the x is ln k. Okay, so here we can easily see that this equation number 1 equation, this Arrhenius logarithm equation, can be easily compared to the straight line equation, that is y equal to mx plus c. Okay, y equal to mx plus c. Okay, so here y is equal to ln k and x is 1 by t, and here the slope, that is the m, is minus ea by r, and here the intercept, that is c, is ln A. As here the slope is negative, so the graph will be, that is ln k versus 1 by t, the graph will be in the negative direction. So it will start from the higher region, as it is not going from the 0 0, that is the starting point, or from the origin, because it is an intercept, and the intercept is ln A. So this will start from here and it will go like this, and this is the, and this intercept is ln A, this is ln A. And what will be the slope? The slope will be, minus ea by r. Okay, although I am writing this in a small space, I have made a slide on that. Here in this slide you can easily show that, but I am showing you how you can draw a graph based on a straight line. Okay, you can do any graph based on the parabola, hyperbola, or straight line equation. Okay, so this is the required graph of Arrhenius equation, ln k versus 1 by t. This ln k versus 1 by t, this graph is highly important, not only for your upcoming exams but for also your competitive exam as well. Okay, so in this class I have explained some topics of chemical kinetics, especially the topics, the name of the topics are activation energy and the graphical representation of activation energy, as well as the Arrhenius equation and the graphical representation of Arrhenius equation. Here in this chemical kinetics, the graphs are very much important, because there will be a certain question on the graphs as well, which consist of 2 to 3 marks even. Okay, so at least 2 marks will be there. So it is very much important for your perspective that you should know the graphs and understood the graph very clearly, so that you can clearly do that. Okay, so I hope you have understood this part very well, and if you have any doubt regarding this class, you can ask me in the comment section below. Okay, so thank you very much. Bye.